So welcome to the next lecture of selected topics in graph theory. Today we are continuing with expanders. During the last lecture, we defined that we are working with deregular multigraphs. We looked at the adjacency matrices and we were discussing the spectrum of the adjacency matrix, which is the set of eigenvalues. And we argued that there is always a complete set of n eigenvalues, and that these eigenvalues somehow reflect the connectivity in a graph in some well-defined way. And this connection between the connectivity of the graph and the concentration of the spectrum around zero is expressed through a connection between edge expansion and vertex expansion and the extreme values of the spectrum. So this is what we ended up with during the last lecture. So let me remind what was the topic. So we were looking at two values of an expansion of a graph: edge expansion and vertex expansion. Yeah. Corresponds to vertex connectivity and edge connectivity in some sense. So edge expansion is the following value. If I look at the graph G and I'm looking at any subset of vertices S, which is pretty small in the sense that it contains at most n-half vertices of the graph, I can count how many edges are sticking out of this subset. So how many edges are here, yes, that have one endpoint in the subset and the other endpoint outside of the subset. So this is the size of the edge set between S and the complement of S. So now for a set S, I can measure how many edges are there, and I can normalize it by the size of S, yeah, because larger sets should expand more. So this is the minimum value of this is the edge expansion. So in other words, a graph has a large edge expansion if every set of vertices S expands a lot, in the sense that there is a lot of edges protruding from it. So vertex expansion is a similar animal. It works like that for a again for a set S in a graph of size at most n-half, I can think of starting a one-step random walk, a one-step walk in some vertex of a graph of the subset, and looking at all the vertices I can reach within one step. Yeah, so this gamma of S, this is a set of all vertices U that can be reached within one step from some vertex of S. Yes, I start with some vertex V of S, I make one step inside the graph, and all the vertices that I reach in this way, this is my gamma of S. And what we argued last time is that gamma of S, if the graph is deregular, is of size at least the size of S. This was easy edge counting argument. So then the vertex expansion of a graph is defined as how many new vertices I see after one step of a walk starting from S, again normalized by S. Good. So these are the two combinatorial notions that somehow reflect how much the graph is connected. And the idea was that these combinatorial notions are tightly connected with the spectrum of a graph through so-called Cheeger's inequalities. So recall that the spectrum of a graph consists of all the eigenvalues, so lambda 1, lambda 2, and so on, lambda n. This is the spectrum. And lambda 1, in case I've got a deregular multigraph, is always equal to D. The largest eigenvalue is the regulator of a graph, and this whole spectrum is in the interval between D and minus D. And these spectral gaps are essentially telling us how lambda 2 and lambda n are sitting inside this interval. Yeah, so here is D, here is minus D, here is this one largest eigenvalue, and the graph has good spectral properties if all the other eigenvalues are in some small, strictly smaller interval somewhere here. Yeah, so lambda 2 is the second largest eigenvalue, and I will commonly denote by lambda the maximum absolute value of the second and the last eigenvalue. Yeah, so the last is here, the second is here. So this essentially tells you how wide is this interval where all the non-trivial eigenvalues are are sitting. So then the idea is that the edge expansion of a graph corresponds to the gap between lambda 1, that is d, and lambda 2, yes, and the vertex expansion corresponds to the gap between d and lambda, so the largest absolute value of a non-trivial eigenvalue, in the following sense, that the edge expansion is sandwiched between a function of the spectral gap of the spectral gap and another function of the spectral gap, and similarly the vertex expansion is sandwiched between a function of the absolute spectral gap and again the absolute spectral gap. Yeah, so the absolute spectral gap is d minus lambda, and the spectral gap is d minus lambda 2. Good. So this is what we ended up with during the last lecture. So there are here 4 inequalities. And the goal of this lecture is to prove those 4 inequalities. So this is what we will be doing during this lecture. Let me just recall one thing about these inequalities. These inequalities show that edge expansion and vertex expansion are functionally equivalent to those spectral gaps, in the sense that the spectral gap is bounded away from 0, is larger than some epsilon, some positive epsilon, if and only if the edge expansion is bounded away from 0 by some positive delta, yeah, depending on epsilon. And similarly for the absolute spectral gap and the vertex expansion. Yeah. So our goal for this lecture is to prove inequalities 1, 2, 3, 4, and we do it because, well, this is a fundamental result about expanders that relate combinatorial notions with spectral notions. But also it also shows basic techniques of working with those animals. So these 2 inequalities will be not that hard. We have already seen reasonings like that. Essentially what we'll be trying to do, we'll be trying to, assuming that the spectral properties are good, we'll be proving that every set of vertices expands well, and this will be done by taking appropriate vector associated with the subset and analyzing how it should expand. This will be an interesting inequality because it is an inequality that is somehow reversed. Yeah, based on the fact that the edge expansion is large, we will be trying to prove that that actually every vector in the whole vector space needs to expand in some sense. So this will be a tricky proof. This inequality 4, actually this is not a tight inequality, and some of the better inequalities here are known, but we'll be actually cheating a little bit. Namely, we'll actually derive 4 from 2 via a trick. I hope that you will appreciate it. Good. So we have 4 inequalities, so let's get to work. So inequality number 1. Yeah, we need to prove that the edge expansion of the graph is lower bounded by half of the spectrum. And yeah, as I said, this will be a reasoning that we have already sort of have seen. And namely, what we need to prove is that whenever I've got some subset of vertices consisting of at most half of the vertices of the graph, then there is a lot of edges sticking out of this subset. Yeah. The size of the edge set of the set of edges between S and the complement of S must be at least the size of S times this lower bound that is here. This is exactly rewritten the claim. Yeah. So then the main idea is to try to understand this term, the number of edges, through algebraic notions. Yeah, so let 1 on S be the vector of where I put 1 on vertices belonging to S and zeros on the complement of S. Yeah, so this is a vector from from R to the n. Yes, that is the indicator vector, indicator vector of the set S. Yes, and then the one on the complement of S is simply the vector of all ones minus the vector of ones on S. Obvious. And then this is an equality that we have already seen during the last lecture. If I want to count the number of edges between S and the complement of S, I can take the following cross product, scalar product of two vectors. Yes, I can take one on ones on S. I can apply my adjacency matrix to it. Yeah, this is the adjacency matrix of G, and I take a cross product with the vector of ones on the complement of S. So how to view this? So this is the same as 1 of S transpose A1 as complement. Yeah, so this is just rewriting this in terms of in the matrix form. So now this is the same as summing Aij, yes, and I put a 1 if I is from S, and put a 1 if J is from the S complement. Yeah, so in this way, if I look at the summation here, I exactly count the total number of edges where this term evaluates to 1, yes, meaning the one of the vertices belongs to S and the other belongs to S as complement. I prefer also to view this equality in a more combinatorial way, namely, what is actually this animal? Yes. So first, 1 on S is like putting ones on the vertices of S. Yes. Now applying A is this idea that I'm essentially making a random walk from every vertex of S. Yes. So applying A means that every one that is there on the vertex sends this one to all its neighbors. Yes. So this is so the vector I get is exactly 1 A times 1 of S. Yes, if every vertex from S sends a 1 to all its neighbors. And now if you make a scalar product with 1 on S complement, then you exactly count if I put an agent on A on the vertex of S, and I take any edge going out of the vector, going out of this vertex, and I check if I end up in a vertex from S complement. Yes, because these are exactly the ones that will survive in this cross product. So this exactly counts the ways of starting in the vertex of S and ending after one step of a walk in the vertex of S complement, which is just the number of edges between S and S complement. Good. So this is a combinatorial understanding of this cross product. Anyway, so I hope that you see this equality here. Yeah. So yeah, we have now understood the combinatorial notion that we are working with in terms of a algebraic notion. Yeah. So let's now focus on this term, and let's try to understand it. Yeah. So first of all, I know that 1 on S complement is simply 1 minus 1 on S. Yeah. So I can rewrite this cross product in the following way, using the bilinearity of the cross product. So now, what is this animal? Here, now A is a symmetric matrix, so I can move A to the other side of this, and A times 1 is simply D times 1. Yeah, because the graph is irregular. Yeah, so 1 is a eigenvector with eigenvalue 1. Yeah, so here is D times 1 on S cross product 1, and well, this cross product just counts the number of ones in the vector 1 on S. Yeah, so this is just the cardinality of S. Yeah, so here I've got D times the cardinality of S, and here I've got minus this term. Yeah. So a cross product of 1 of S with itself, but to one of the sides I apply A. Yeah. So now comes the usual trick that we are doing. Yes, we are now decomposing the vector of ones on S into a parallel part and the perpendicular part, where parallel part is the part that is parallel to to the vector of all ones, and the perpendicular part is the part that is perpendicular to the vector of all ones. Yeah. So here is the direction of the vector of all ones. Yeah, and here was 1 on S. So then 1 on S parallel should be just the projection onto the direction of all ones. Yes, and here is again this formula for computing the projection. Yeah, so you've got this term cross product of 1 of S times 1, which is just the cardinality of S again, and cross product of 1 with itself, of the vector of all ones with itself, which is just n. Yeah, so this is just 1 times this scaling factor, size of S over N. Yeah. And then the perpendicular part is just the rest. Yeah, so this is just 1 minus the, sorry, this should be 1 on S, of course. Good. So let's rewrite our what we were concerned about. So let's rewrite this scalar product here. So if 1 on S can be rewritten as a sum of these two vectors, I can rewrite it as the sum of those amazing 4 terms here. So fortunately, 2 of them are actually cancelled out. This one is 0 and this one is 0. Why? Because this vector is parallel to all ones, and this vector is actually perpendicular to all ones. Yes, because this one was perpendicular, and the vector, the subspace of vectors perpendicular to all ones is an eigenspace of the matrix A. Yeah. So fortunately, this one is 0 because these two vectors are perpendicular, and the same this one. So now this animal is also quite easy to understand. Well, because this is just 1 times the size of S over N. And the same here. This is actually 1 times the size of S over N, meaning this vector here is this, yes? And applying A to it just multiplies by D, yeah? Because again, the vector of all ones is an eigenvector of eigenvalue D. Yeah, so now this is, I can rewrite it like that. Yes, I can move this D times S square over N square in front. Yes, and I end up with the scalar product of 1 with itself, which is just equal to N. Yeah. So I end up with this animal here, and the remaining animal that I still need to understand is this scalar product of the perpendicular part with itself. Yeah, with A in the middle. Good, but why was this? Why we did all of this? Namely, this animal here, we can understand quite well because this is this quadratic form AU product U for a vector U that is actually perpendicular to all ones, and this was the main idea, because for all such vectors we know stuff about how this kind of product works. As you if you remember from the last lecture, we know that lambda 2 is equal to the maximum over all vectors U perpendicular to all ones and non-zero of AU cross product U over U cross product U. Yeah, so this is how much like applying U can prolong in the direction of U in some sense. Yeah. So what we know is that for every vector perpendicular to U to all ones, we have this inequality. Yes, that this term is upper bounded by the norm of U square times not D, but actually something significantly smaller times lambda 2. Yeah. So this is just the square of the L2 norm of vector U. So I've got this inequality. Yeah. So this is actually well understood in the spectral terms. Yes, how we can upper bound this term. Okay, so now given this understanding, we can try to understand this inequality. So for this, we need to understand what is also the L2 norm of this perpendicular part. Yeah, so this perpendicular part by the Pythagoras theorem is just the square of its norm is equal to the difference between the squares of the norms of all ones on S and on the parallel part. Yes, so this one is easy to to see. This is just a vector of S1s, so the square of the L2 norm is just S, yes, because S times I add up once. And this one, recall that this is 1 times the size of S over n. Yeah. So if I now sum up n times the square of the scaling factor, yes, I get exactly this. This is S square over n. Yeah. I can now take S in front and end up with this equality. Good. So to summarize, what has happened? There was quite a lot of computation, but essentially all of this computation was in order to understand the consecutive terms in spectral manner. Yeah. So we started with the total number of vertices between S and complement of S. Yeah. We understood it in algebraic terms as this difference. Yeah. This was here. Yeah. Yeah. So now we rewrote this scalar product using the parallel part and the perpendicular part. So the parallel part ended up with this kind of a term, and the perpendicular part is still hanging there. And then we argued that this remaining perpendicular part, this sort of error term in some sense, can be bounded in this way using the norm of the perpendicular part and the second eigenvalue. Yeah. So this norm we have also understood like that. Yes, as being equal to simply the size of S times the scaling factor. So we have this inequality here now. Yeah. So now magically I see here this term and this term that I can move to the front. Yes, here, and I end up with this. Sorry, this was actually, yeah, this one is taken to the front, and I end up with the difference between D, yes, coming from here, or rather from here and from here. So this is this kind of a regular part, and the error part is only bounded by lambda 2. Yeah, so here we capitalize on the fact that we understand that lambda 2 has to be significantly smaller than D. Yeah, so now I end up with D minus lambda 2 in front. So now finally I can use the assumption that the size of S is at most n½ to understand that this term, 1 minus the size of S over n, yes, is actually at least 1/2. Right? So now this justifies this inequality, and I am done. Good. Any questions about this proof? Maybe some +1s on the chat too, if you are happy with the proof. Okay, I see some +1s, but not too many of them. Can I clarify something? Okay, if not, then maybe we'll continue with the next proof. Good. So this was a basic a basic proof that essentially relates a combinatorial term to a spectral term and uses a good understanding of the spectral properties of the matrix in order to prove something combinatorial. Yeah. So now we are trying to do something reverse in the sense. Yeah. So we are now proving the second inequality. We are upper bounding the edge expansion by the spectral gap. Yeah. So in other words, we are trying to do something reverse, in the sense that we need to prove a lower bound on D minus lambda 2, a lower bound on the spectral gap, knowing that every set in the graph expands a lot. Yeah, so knowing that the edge expansion is large, we need to prove that the spectral gap must be large. Yeah? So how do we do this? We take a, say, eigenvector x with this corresponding to this eigenvalue lambda 2. Yes, and we need to understand, we need to, using the fact that some of the sets are expanding a lot, yes, that all of the sets are expanding a lot, prove that actual lambda 2 must be pretty small, or in other words, d minus lambda 2 is pretty large. So just to recall, the fact that x is an eigenvector with eigenvalue lambda 2 means that ax is equal to lambda 2 times x, and because this is a vector that is from this basis of orthonormal basis of eigenvectors, this vector is orthogonal to the vector of all ones. Good. So now we are trying to look at this vector x and try to understand it somehow a bit combinatorially, because we want to now use the assumption that the edge expansion is large. Okay, first of all, let's normalize it a little bit. First of all, I can assume that at most half of the entries of x are positive. Yeah? Because, well, I can always take x or minus x, right? One of these two vectors has at most half of the entries positive. So let me take the one that is that has this property. Yeah? So this I can assume. Also, because so far I did not break any symmetry regarding the vertices, let me order the vertices so that the entries of x are ordered like that. x1 is larger or equal than x2 is larger or equal, and so on up to xn. Yeah. So this is more or less how x now looks in this way. First, there are some positive terms. Yes, there is at most half of them. Yes, then maybe there are some zeros. Yes, and then there are some negative terms. Right. So now the crucial idea in the proof is to look at the following vector y. Vector y is like the positive part of x, in the sense that whenever xi is larger than 0, I simply take xi, yes, and whenever xi is non-positive, I replace it with 0. Yeah, so y is something like x plus. Let's call it like that. Yeah, so I look at the positive part of x. Yeah, this is y. So note that because I assume that at most half of the entries of x are positive, this means that for all the second half of the entries of y are actually 0. Yeah, so most of the entries of y are 0. So now the main idea. Yes.
Shouldn't this inequality j greater or equal and half be strict?
You're asking difficult questions. You are probably right. Yes. Thank you. Indeed. Okay. So the main trick of the proof, and I must say that I do not have enough intuition to say why this trick works, but it works, is to look at the following magic value. B equal to, I look at all the edges of the graph. Yeah, so for instance, an edge like that between vertex I and vertex j, and I sum up yi square minus yj square. Yeah, note that this is actually positive, not negative, because we assumed that that this vector is x is descending, meaning non-increasing, so the vector y is also non-increasing. Yeah. So this is the value that we will study, and we will try to rewrite it in two different ways: one combinatorial way and one spectral way. And the equality between these two ways will give us the proof. Good. So let's first look at B combinatorial. So let's make a combinatorial analysis how to rewrite B in a nice way. So first of all, if I sum up these terms yi minus yj, I can rewrite this yi square minus yj square into a telescopic sum. So if I have this, say, maybe I will draw this arc a little bit longer. Maybe j is here. Yes. So if I'm having this yi square minus yj square, instead of this, I could write yi minus yi plus 1 square plus i plus 1 square minus yi plus 2 square and so on and so on. Yeah, so instead of taking this whole difference at once, I divide it into the sum of several differences that sum up in a telescopic way. Yeah. Okay, so now given this, I can rearrange the sum, because now I can focus on one of those terms, say yi minus yi plus 1 square, yes, and I can understand how many in total this term, how many times it appears in this sum. Well, how many times? If I draw a perpendicular line between vertices I and I plus 1, I just need to count how many edges are crossing this line. Yeah, because this term will appear in this in this telescopic expansion for exactly those edges. Yeah. So in other words, I can rewrite this sum by changing the order of summation into a sum from I equal to 1 to n minus 1 of, well, this this term times the number of edges between the prefix si and the suffix si complement. Yeah, and this is perfect because this is a combinatorial term we are interested in. Yeah, or in other words, we know that the set S expands a lot. Si expands a lot, so there is a lower bound on this term. More precisely, I can now write that, well, the size of the number of edges between Si and Si complement is at least the size of Si times the edge expansion. Yeah, this was the definition of edge expansion, and the size of the prefix is simply I. Yeah, so I have this inequality here. You need to be a little bit careful here because in the assumption about edge expansion, we assume that this works for all the sets of size at most and half. But this is fine. Why? Because we know that these yi's are anyway 0 in the second half. So these terms are always 0 for I larger than n-half. Yes, so I can still rewrite this inequality also for such y's because they will be anyway multiplied by 0. Good. So now I justified this inequality. Yeah. Okay, so this is already a pretty difficult thing. So let's try to understand what it actually is and how can we rewrite this sum. So first of all, the edge expansion is a fixed multiplier here. So let's put it in front. Yeah, and let's actually try to rewrite what is here. Yeah, so the first term is simply y1 minus y1 square minus y2 square, right? The second is y2 square minus y3 square, but multiplied by factor 2. The third one is like this, but multiplied by factor 3, and so on and so on. The last one is multiplied by factor n. But now note that I can now, instead of grouping the terms like I did here, I can look that here there is a y2 square and another y2 square, just with a one larger coefficient here. Yeah? So this y2 square here cancels out with one of those. Yeah? And this twice y3 square, it cancels out with all but one of those, and so on and so on. So eventually, all of those will cancel out apart from this last term minus n times yn squared. But well, yn square is anyway equal to 0, right? Okay, so if I do all this canceling out, yes, from each of those two consecutive guys, exactly one survives. Yeah, so I've got simply y1 square plus y2 square and so on plus yn square. And if I did not think about this, I would need to subtract n plus 1 times yn square, which is anyway equal to 0. Yeah, good. So that's perfect because now this thing, this animal here, is nothing else than the L2 norm of y square. So we have proved that our term B can be very nicely lower bounded using the edge expansion. So this is just the edge expansion of G at least times the square of the L2 norm of Y. Good. Any questions about this tricky analysis here? Okay. If not, then let's continue with the spectral analysis. So now we are looking at our term B, and we are trying to rewrite it so that we can relate various components of this term to the spectral properties of the matrix of the adjacency matrix. So yeah, recall that B is equal to this, so the sum of over all the edges of the difference between the squares of the entries in Y. So now I can use this basic formula to say that this difference of squares is the difference times the sum. Yes, and now I can apply Cauchy-Schwarz. Yes, to separately look at the term corresponding to the differences and the term corresponding to the sums. Yes, so let this term be equal to B1, let this be B1, and this be equal to B2. Yeah, and we will be now, so before from the combinatorial analysis we have a lower bound on B, now we are trying to make an upper bound on B, yeah, based on spectral properties. Yeah, so now we will estimate B1 and B2 separately. So B2 will be the simpler one. Yeah. Let's look at this. So B2 is simply the sum of this square of the sum of the entries. Yeah. So now I can use a very basic estimation that A plus B square is upper bounded by 2A square plus 2B square. Yeah, this is a geometric arithmetic mean if you open the brackets here. So I can estimate it like that. Yeah. So and this was in order to separate y's, yi's, and yj's inside the sum. Because now if I look at the sum, this called sum, I can think how many times a particular yi appears in the sum. Well, how many times a particular 2 times yi square appears in the sum? Well, as many times as the number of edges incident to I. Yes, because every edge is corresponds to one term of one endpoint and one term of the other endpoint. So how many terms are there for one particular vertex? As many as the number of edges that contributes to it. Yeah. So all of this can be rewritten as simply 2 times d. Yeah, d comes from the regularity times the sum of squares. Yeah, a sum of squares is nothing else than simply the square of the L2 norm. Yeah, so all in all, we have here that B2 is upper bound by square root of 2D times the L2 norm of the vector Y. Good, perfect. So we have already see here L2 norm of vector Y, here L2 norm of vector Y appearing on both sides, and there is some relation here. So now we come to the crucial term, the term B1. And this is the term where we have all those differences, and this is a term where actually we will see the spectral properties kicking in. So again, I open I look at B1. This is equal to this by definition. Yeah. So now I open the brackets. Yeah. So I've got this term here. So the squares, you can treat them the same way as before. Yeah. So this sum of squares, they sum up to d times the sum of squares. Yes, which is d times the norm of y square. Yeah. And still I have this the difference with twice the sum of the products, and this is a term that is interesting. Yes, this is a term that somehow mixes different vertices with each other, and therefore it corresponds to something that spectrally is interesting. So indeed, we can rewrite this term, yeah, 2 times the sum in the following way. This is nothing else than A applied to Y, scalar product Y. And this we have seen already a lot before, yeah, because this is the same as the sum of, well, let's write it like this, Y transpose AY, yes, which is the sum of Aij, yeah, these are the entries of matrix A, Yi, Yj. So now this is the same as this, yes, because here here observe that every edge is actually counted twice. Yes, once for the one entry, once for the other. Good. So we have already seen, we now see that this term, the sum of products, is actually understandable in terms of the scalar product here. And this scalar product is this scalar product that we are actually concerned when we are talking about lambda 2. Yeah, because we know, again, lambda 2 is the maximum over all u perpendicular to all ones, yes, of a u over u. Yeah. Okay. So now comes another trick regarding the analysis of the scalar product. Because so far, well, recall that y was not really in perpendicular to all ones, right? Because x, the eigenvector of corresponding to eigenvalue lambda 2, this was the vector that was perpendicular to all ones. However, y was this positive part of x. Yeah. So how can we actually look at this and use the spectral property if y is not in the vector orthogonal to all ones? Well, observe that, recall what was x. X looked like that. It had first some positive values, then some negative values, and some zeros in between, and y was the positive part. So first of all, y is a positive vector. Yes, sorry, non-negative vector. It has only non-negative values. And if I now look at the vector y minus x, yes, how it works, well, these pluses, they are actually equal to each other, meaning these entries. So all these cancel out. The zeros here also cancel out. And now from these zeros here, I subtract these negative terms here. So they are actually positive. Yeah, so this is how vector y minus x looks like. So this vector is also non-negative. It has also non-negative entries. Yeah? So if I look now at this scalar product of a y cross product y minus x, then this value here is non-negative, because in whole this summation, I only consider non-negative terms. Yeah, because y has only non-negative terms, y minus x has only non-negative terms, and of course the adjacency matrix also has only non-negative terms. So if I now rewrite this using bilinearity, this means that this, the scalar product of y, a applied to y with y, is not smaller than the scalar product, ay cross product x. So this means that d equal to this, yes, is at least equal to ay cross product x. Now I can move this guy here, because A is a symmetric matrix, yes, and I've got this. Yeah. And now I apply the fact that actually x was the eigenvector corresponding to eigenvalue lambda 2. So I can just rewrite ax as simply lambda 2 x. Yeah, I put lambda 2 in front, and I have now here y cross product x. And now y cross product x, this is a funny thing. This is the same as y cross product y. Why? Because, well, if I now make a cross product of y and x, it doesn't matter whether I multiply some negative terms with zeros or I multiply zeros with zeros. Yeah. So this is just the same summation. So I just justified this equality. Yeah. And again here, this is nothing else than the norm of y squared. So we arrive at this. So this d is lower bounded in terms of the second eigenvalue and the norm of y squared. So now we can piece all these calculations together. So we were looking at the value b. On one hand, we had a combinatorial analysis that was looking at this expansion of the prefixes of y. that showed that the value of b is lower bounded by the edge expansion times the norm of y squared. On the other hand, b could be rewritten, sorry, here there should be inequality. Yes, it's upper bounded by Cauchy-Schwarz by the multiplication of two terms, b1 and b2. For b2, we had a pretty easy upper bound of the form square root of 2d times the norm of y. And for b1, we had a more involved upper bound of this form where d was this ay cross product y. Okay. And finally, we understood that d is at least this. Okay. So now we can rewrite it. Meaning we can use this estimation to show that this term is smaller or equal than this. Yeah. And voila, I put y, the second norm of y in front of everything, one from here and one from here, and I've got what I want. Square root of 2d times the spectral gap. So there's one more detail here that needs to be argued, because in order to get the final inequality, I actually need to divide both sides by the norm of y squared. And for this to work, I need to make sure that actually this is a non-zero vector. But observe that x was non-zero. Well, it was a eigenvector, so it better be non-zero, and was also perpendicular to all ones. Right? So if I have got a non-zero vector that is perpendicular to all ones, it needs to have both positive terms and negative terms, and positive entries and negative entries. So the positive part of x is actually non-zero. Yeah. So now y is a non-zero vector. I can now divide by the square of its norm, and I get what I want. The edge expansion is a lower bound for the term 2d times d minus lambda. And this proves the second inequality. Good. Any questions? And otherwise, please put a +1 if you're happy with the proof.
Do we allow loop edges in this proof?
Sorry?
Do we allow loop edges in this proof?
Yes. We allow loop edges in this proof, and nothing goes wrong as far as I remember. Okay, I see some +1s, not too many of them. Maybe should I repeat something or clarify something? Okay. But anyway, I can let's just move on to the next proof. Yeah. So now we are going to work with with vertex expansion. So far we understood the edge expansion both from the point of view of lower bounds and the proof of upper bounds on the edge expansion in spectral terms. So now we are going to work with vertex expansion. Yeah, and so we in particular we're going to prove this lower bound. Yeah, and recall that now lambda is the maximum value or the maximum absolute value of non-trivial eigenvalue of the matrix, and it is I can also view it as I look at the space of vectors orthogonal to all ones, and I see how much the application of I can prolong the vector in L2 norm. Yes. So we argued during the last lecture that lambda can be understood also like this, and this is how we will understand it. So now we are going to prove this inequality, and the proof will be kind of similar to the proof of lemma 1 that we gave at the beginning of the lecture, because again, what we are trying to do, we are trying to show that every set of vertices expands a lot. Yes. And the tool that we have for this is that we know that the second eigenvalue is the absolute spectral gap is large. Yeah, so within this eigenspace of vectors orthogonal to all ones, the vectors are prolonged on the slide. Okay, so this is how we are going to do this, and the main, let's say, problem or issue that we will be facing is that how to understand the edge expansion in algebraic terms. Yeah, so recall that what we are given is a set S of size at most half, and we are thinking about the edge expansion of this, which is this animal, the number of vertices I can access in one step from a vertex of S minus the size of S. So this is like how many new vertices you see after one step of a walk, normalized by the size of S. Yeah. So firstly, we need to understand how to phrase this animal in algebraic way. Yes, because we need to relate it to some vector. Yeah. So recall that this one, that the gamma of S is the set of all the vertices for which there is a vertex of S, such that you can be reached from it within one step. Yeah. So in other words, if I start by putting ones on the vertex of S, and then I applied my matrix A, the adjacency matrix, in this way I get a non-negative entry exactly at the vertices of gamma. Yeah. So the vertices of gamma of S are exactly all the indices I, such that the entry corresponding to the index I in the vector A times the ones in S is positive. Yeah, so this is exactly this idea that I put ones on the S, and applying A distributes, like sends all these ones to their neighbors. Yeah? So in other words, gamma of S is nothing else than the support of this vector. The support of a vector is the set of indices on which the entries are non-negative. Are non-zero. Yeah. So now we understood gamma of S in algebraic terms as the support of some vector. Okay. So again, we will be looking at some particular value. The value will be B, like that. It will be simply this one. I take this vector of interest because this vector will help me to in getting the size of gamma of S into the equation. Yes, and I make a cross product with simply all ones. So on one hand, it's very easy to see what this vector actually is, because A is a symmetric matrix, so I can just move A from here to here. So B is equal to Y on S times A times 1. We have actually seen this argument already before. A times 1, this is simply D times 1, yeah, because the graph is irregular. So I've got this, yeah. I can put D in front, and this scalar product just counts the number of ones in the vector of 1 on S, yes. So I get simply D times the cardinality. Okay, so on one hand, B is actually equal to a very, very, very understandable value. Yeah, D times the size of S. On the other hand, I can start to think about B spectrally using Cauchy-Schwarz again. Yeah. So B, yes, equal to this vector. Yeah. So now know that this vector, the support of this vector, is equal to gamma of S. Yeah. So instead of taking a cross product with ones everywhere, I can take a cross product with ones on gamma of S, yeah, because all the other entries are 0 anyway. Yeah. So now that's a crucial part that allows us to put gamma of S into the picture spectrum. Yeah, because now I can apply Cauchy-Schwarz, yes, to say that this is upper bounded by the norm of this first vector times the norm of the second vector. Yeah. The norm of the first vector, let me so far put it here and not meddle with it. However, the norm of 1 on gamma of S, this is L2 norm, of course. Yes, this is nothing else than I sum 1s over gamma of S, actually 1 squares, and take a square root. So this is just the square root of the size of gamma of S. Yeah, so here. So perfect, because now this this observation with the support allowed us to make an upper bound on B that involves the term that we are actually interested in. Yeah, and the remaining term here, yes, this is actually a term that we can try to understand at least spectrally. Yeah, because this is I look at some vector, I apply it A to it, and let's try to understand what is its second norm. So we have already seen how to do this, right? Actually, this is the third time we are doing this trick. We are now decomposing 1 on S into the parallel part and the perpendicular part. The parallel part is again the projection onto the direction of all ones. So this is just all ones times S over N. Yes, and the perpendicular part is the rest. Okay, so now let's try to understand what is this animal, because this is the term that we still do not understand fully. Yeah. So first of all, so this A on S, A applied to ones on S. This is the same as A applied to ones on S perpendicular parallel plus this A applied to 1 on S perpendicular. Yeah. So now observe that these two vectors, they are orthogonal to each other. Yeah, because well, before the application of A, they were orthogonal, and each of them is within a two orthogonal eigenspaces of the matrix A. Yeah, so A only acts in the direction of all ones on here, and A acts only in the eigenspace orthogonal to all ones in here. Yeah, so these two vectors are orthogonal, so I can use Pythagoras theorem to say that this norm square is equal to this sum of squares. Okay. Okay, so as usual, this term is very well understood. We actually already very well know what is this vector. This is S over N. Okay, maybe not. Okay. We know that this is this is S over N times all ones. So application of A to it only prolongs it d times. So this justifies that this term is the same as this term. Yeah, because application of A prolongs it d times. So in the square, I've got an additional d square in front. Yeah, and here I just rewrote the remaining. Okay, so now comes the spectral part. Namely, we know that now this vector is orthogonal to all ones. Yes. So application of A, how much it can prolong the length of this vector at most lambda times. Yeah, this is this fact that the psi, this over the norm of U is at most lambda. Well, is at most lambda for each U that is orthogonal to all ones. Yeah. So this justifies this inequality. Yes, I've got this plus lambda square times times the norm of the orthogonal part square. Yeah. Okay, so what was the norm of the orthogonal part square? Well, let's rewrite the orthogonal part in more understandable terms. This is just the difference between the whole vector and the perpendicular part, and because these two, this guy and this guy, they are orthogonal to each other, I can use again Pythagoras theorem to say that this norm square is equal to the difference between these squares of norms. Okay, perfect. So now if I rearrange all the stuff, I can move this part to the other bracket and put summand corresponding to the or perpendicular, parallel part with the coefficient d square minus lambda square, and have the have a summand corresponding to the whole vector being lambda square times the size of the 1 from S norm square. So now let me recall what were actually those vectors, right? So this is one. This vector was 1 on S. Yeah. So its norm square is simply the cardinality of S. No surprise. Yeah. So this vector was the vector of all ones times the factor size of S over N. Yeah. So if I take this norm square, this means that I n times sum the term S square over N square, which gives me S square over N. Perfect. So I've got this. Great. So now comes the part where we actually recall that there was some assumption that we had. There was an assumption that S is at most n square. Sorry, n half. Yes, we are measuring the expansion of only small sets. So this means that S over n. This means that S over n is at most 1/2. So I can take S over n from this term, and I can upper bound it by 1/2 here. Yeah. So this justifies the transformation between these two terms. Yeah, the other term is still there. Yeah. So if I now put S in front, I get here a multiplier d square plus lambda square over 2. Oof. So what is the conclusion of all of this? On one hand, we looked at D, and on one hand, we have seen that combinatorially, this is very easy to analyze. It's actually equal to D times the cardinality of S. On the other hand, we used again Cauchy-Schwarz, yeah, to relate it to two terms. One of them had the support of A times 1 on S here that was actually equal to the size of gamma S square root. And there was another term here, the length of A times 1 on S. And this one we managed after this decomposition and spectral analysis to upper bound by such a thing. Yeah. So all in all, if I now forget about this B inside, yes, and I square this inequality here, I get this. This is squaring and canceling the S on both sides. Yeah. So now I can say that the ratio between the size of gamma of S is at least 2d square over d square plus lambda square. Yeah. But recall that actually we are not concerned about the ratio between gamma of S and S. We also wanted to subtract the size of S to see how many new vertices I see after one step of expansion. And if I now subtract 1 from both sides, on this side I get what I wanted. On this side I get 2d square minus d square minus lambda square, which is exactly the term I promised at the beginning. Good. So this was this amazing calculation here. But again, this is the same principle as before. Yeah, we are trying to understand the vertex expansion in algebraic terms. Yes, and then we are using some Cauchy-Schwarz inequality here between carefully prepared vectors in order to introduce the term we are interested in into the equation. And now the remaining term here, this norm here, this can be understood in spectral terms using the assumption about the absolute spectral. So this is what conceptually happened here. Good. Any questions about this proof? And otherwise, please put a +1 if you're happy with the proof. Okay, can I clarify something? I do not see that many +1s. Okay, anyway. Also, there are not that many of us here. Yeah, so let's move to the last lemma, lemma 4. This is an upper bound on the vertex expansion in terms of the absolute spectral gap. And here will be, as I said, we will be cheating. Namely, this will be a purely combinatorial proof that will actually use lemma 2, so the proof for the edge expansion in order to reason something about vertex expansion. And there will be a trick here that will be actually very fruitful during the next lecture. So, so please pay attention. So the idea is that instead of looking at the graph G, we will be looking at the graph G square. What is the graph G square? The idea is that we take the graph G, and for every walk that I can, every walk of length 2, say from a vertex U to a vertex V to a vertex W, that is there in graph G, we put an edge UW in G square. So maybe some example, if my graph G is, say, a path on 3 vertices, yeah, what will be G square? Yes, well, we will have those 3 vertices. Yes, so the vertex set is the same. And now we are putting one edge for every walk of length 2. Yeah. So what are walks of length 2 here? So definitely you have a walk from here to here. Yeah. So chach. Yeah. So here is an edge. But also there is a walk back. Yes. So from W to U, there's also, so there will be actually a double edge here. Yeah. No, sorry. Maybe let's make it regular so that I do not miss something. Let's make it a triangle. Okay, so yeah. Sorry for the mess. So let's understand for any 2 vertices, say U and W, how many walks, how many edges there will be between them. Yeah, there's one walk between U and W here. Yeah, so I can first choose this edge and then this edge. So here I will put one edge for this walk. Yes. Then U will be also adjacent to V because I've got a walk like that. Yes. But also from U, I can walk to W and back. So this is one walk that contributes to a loop at U. And I can go to V and back, and this will be another walk of length 2. This will be a another loop at U. Yeah. So similarly here, I will have one edge between V and W corresponding with the walk through U. Yes. And there will be also from V 2 walks back to V. So here you've got this. Yeah. So this will, squaring a triangle gives you a triangle. However, every vertex is also additionally 2 loops added to it. Yeah. So observe that in this way, this square graph is d-square regular. Yeah, because for every vertex U, how many edges there will be going out of U? Well, there are d ways of choosing the first neighbor V, the first edge I'm going. V, and then from V there are again d ways of continuing with the second step of the walk, possibly going back to U, which will end up with a loop at U. Yeah. So G square is d regular when G is G square is d square regular when G is d regular. And now the crucial point is that this operation, though graph theoretically it looks a little bit strange, spectrally.
Can I interrupt you with question?
Yes.
So we do not have a double edge between U and W and so
on? No, we do not have a double edge between U and W.
Okay.
Yeah. So for every walk like that, for every undirected walk, we put one edge. Yeah, sorry,
Okay,
I mixed this. In some sense, in the adjacency matrix, there will be like one entry corresponding to that U is adjacent to W, and another entry corresponding to W is adjacent to U. Is this clear?
And edges that do not lie on triangles will disappear in the squared graph, right?
What do you mean?
If we didn't have that edge between U and W,
yeah,
there would be no edge between U and V.
Yeah, maybe it's
okay.
good to actually look at this example. Yeah, here. I did not want to do this example because it's not regular and therefore a little bit non-kosher in this.
I guess on a square you would see the same thing. On a square you would see the same thing.
For the square, I would see like that. From U to W, I would see one edge because there is a walk of length 2 between them. Yes. Then from U, I would have a loop here because I can go to V and back. Yes. From W, I would have a loop. Yeah, because I can go to V and back. Yes. And from on V, I would have actually 2 loops. Yeah, because I can go to U and back, and I can go to W and back. So this will be the square of this of G, if G is a path on free vertices. Good. Okay, so G square is deregular if provided G was deregular. Yeah, G square is D square regular, and more importantly, this operation is can be very well understood in terms of adjacency matrix, because the adjacency matrix of G square is nothing else than the square of the adjacency matrix of G. Yeah, because I make one step of a walk and then the second step of a walk. Yes. So this means that if the adjacency matrix is just square, this means that the spectra also just square. Yes. If I've got spectrum of G equal to say lambda 1 lambda n, then the spectrum of G square, being the spectrum of the square of the previous adjacency matrix, is just the set of squares of the eigenvalues. And this is easy to see in several different ways. For instance, if you think about the eigenvalues being, you can decompose the matrix in this orthonormal basis. So there is a matrix B that is an orthonormal matrix, yes, like that, such that you can write A as B transpose, then a diagonal matrix and B. Then G square is nothing else than B transpose DB, again B transpose DB. This stuff cancels out and you get B transpose D square B. Yeah, so squaring the matrix in this orthonormal form just amounts to taking the diagonal and squaring every entry of the diagonal. Or otherwise, you can think of it if you take an eigenvector x of the matrix A and you apply to it A 2 times, A square, then the first application just gives you an eigenvalue in the front, and then the second application gives you the same eigenvalue again. Yeah, so you've got the same basis of eigenvectors, and just the eigenvalues get squared. Yeah, so this means that this is an operation on the graph that really, using which we can really control the spectrum of the adjacency matrix. Yeah. Okay, so let's think about. So this was the spectrum, and now the crucial point is that this spectrum here. Well, these are only positive values, right? Because these are squares. So this means that in here, it is lambda 2 that has the maximum absolute value among lambda 2 and lambda n. Yeah, so there is here the absolute spectral gap is equal to the normal spectral gap. Yeah, because we artificially, by squaring the graph, yes, we just moved all the eigenvalues to the positive part. Yeah. Okay, so now what happens therefore with the vertex expansion? I claim that squaring the graph cannot worsen the vertex expansion. Why? Because, well, if I look at any set S in my graph, and I look at this gamma of S, the set after one step of the walk, yes, we already argued that the size of gamma of S is at least as large as the size of S. So I can find some set T here whose size is the same as the size of S, that is contained in gamma of S. And now if I apply the second step of a walk, yes, it expands to some gamma of T, yes, whose size is well, at least such that is at least the size of T plus the vertex expansion times the size of T. Yeah, this is the definition of vertex expansion. Yeah, so now how much S expanded? Well, it expanded at least to gamma of S, so at least to T, yes, and T expanded as S in the graph. Yes, so this means that the size of gamma of S, say gamma square of S in this square graph minus the size of S over S is at least the size of gamma of T minus S over S, but the size of gamma of T is at least like that, yes, and the size of T is equal to the size of S, so I've got this is at least the vertex expansion. Yeah, so I can just expand once, trim, expand a second time, and say that I expanded at least as much as in the original graph. Good. So so we know now that the operation of squaring a graph does not deteriorate the vertex expansion of the graph. So I can now write it like that. I start with the vertex expansion of G and say that it is not worse than the vertex expansion of the square. Yeah. Now this is quite easy to see that the vertex expansion is never larger than the edge expansion, and this is just counting the edges. Yeah, if I expand to some set of new vertices, I at least have as many edges going to this set of new vertices. Yeah? So I've got this inequality. So now I can use my my 2, yes, my lemma 2, that but for the graph G square. Yeah. So now I relate the edge expansion in G square. I upper bound it by the spectral gap in my graph G square. Yeah, but here this is well, the regularity of G square is D square. So this is this. Yes. And now the second eigenvalue, yes, the second eigenvalue is actually the square of the second up to the absolute value of the eigenvalue of the original graph. Yes, so this is this trick with squaring. Yeah, so here lambda is max of lambda 2 and lambda n, and the trick here is that because of squaring, the second largest eigenvalue of G square is actually lambda square. Yeah. So this justifies this inequality, and we are done. So as I said, by a more precise analysis in a similar spirit as in lemma 2, you can squeeze a better bound here. However, this bound is conceptually good enough, and it can be just obtained by looking at the square of a graph, because in the square of a graph, the absolute spectral gap and the spectral gap are the same, because all the eigenvalues are non-negative. Good. Are there any questions about this proof? Okay, if not, then this is all I wanted to say for today. This was probably the most technical lecture of this whole course, but I hope that it gave you a good understanding of at what kind of tools and what kind of analysis you do to prove things about expanders. During the next lecture, we will actually capitalize on this intuition that we gained here, and we will be proving, we will be constructing an expander. So we will be proving that there exists arbitrarily large constant like deregular expanders for a constant d, and with a good spectral gap. And this will be quite a lot of technical work there with all these kind of estimations. There will be also interesting graph products constructions. However, there will be also quite a lot of conceptual work in how to actually get a larger and larger expanders using some inductive procedure. Good. So next lecture, it will be the so-called zigzag product and zigzag expander construction. Any questions? Okay, if not, then thanks a lot for this lecture.